Welcome back to the last talk of this session. So our next speaker is Giulia Marcucci from Apoha Limited. Yes. She will tell us about unconventional computing by Cnoidal wave collision.
Thank you. Thank you very much. It's such a pleasure for me to be here. I'm very grateful to be invited. And exactly as Elena and Adriano, my talk is more on the way back side. Indeed, today I'm not going to talk about machine learning as a software, but I will talk about machine learning as a hardware. And the way we hope to realize this hardware is using dispersive nonlinear waves. So through this hardware, we are able to build analog computers. So everybody nowadays knows what a digital computer is, but I want to stress some points really to the analog computers, because analog computers can actually be in a world in which the energy consumption is always more an important topic, can actually be the future. Together with quantum computing. So the first analog computer was developed by William Thomson and later first Baron Kelvin, and it was a type predictor developed in 1873. While instead the first digital computer was invented by Atanasov in the 30s. Analog computers are not based on states. So for this reason, they can deal with continuous data, while instead digital computers cannot. Digital computers are based on two states, on and off, or 0 and 1. And for this reason, they can just deal with discrete data. Okay, now I practically finished to list the advantages of current analog computers, because all the other advantages are owned by the digital computers. Indeed, the digital computers are fast, have big memory, have high accuracy, use low powers, and they are easy to use because they are based on binary signals in electronic circuits. On the other hand, instead, analog computers are slow, have no memory, and so on and so forth. They are also difficult to use because they are based on complex dynamical systems. So the question is, and this is the dream, I'm not going to tell you that we solved this problem, it would be amazing, but we are trying to build a computer that is able to merge together the best of both worlds. So a computer that actually deals with continuous data, but is also not only fast, but ultra fast. It has big memory, high accuracy, uses ultra low powers, and is also easy to use, but it's also a lot of fun because it's based on complex dynamical systems. So a computer that is based on a holistic approach, in which the whole is greater than the sum of its parts, and actually uses complexity to solve complex problems. So I really don't have to explain to this audience what an artificial neural network is, but I do want to focus our attention on a peculiar architecture in the world of artificial neural networks, that is the reservoir computing. So the reservoir computing is still an artificial neural network. Indeed, it has an input layer, a hidden layer, and an output layer, but it cannot be considered as a shallow network because the hidden layer is actually a projection of many layers, like the layers that are into a deep neural network. So the hidden layer, the unique hidden layer, is actually giant, and for this reason we cannot really get access to it, and we can just treat this hidden layer as a black box. So what we can do is to train the reservoir in a way that, given a certain input, we get a certain output. And these reservoirs can also be physical, and if they are physical, they are complex dynamical systems. So for my interest, I would say, why can't we use a wave reservoir? So why can't we use propagation of nonlinear waves to build this complex dynamical system? And this is what I'm going to show you. Of course, it's a first work, so it doesn't have the ambition to be complete, but it traces the path to the idea of building a neuromorphic computer using nonlinear wave propagation. And the two systems I'm going to show you are related to Navier-Stokes equation, because in the first system, the reservoir is modeled using the nonlinear Schrödinger equation, while instead in the second system modeled using the KdV equation. The nonlinear Schrödinger equation is the approximation of the Navier-Stokes equation in deep water, and the KdV equation is the approximation of Navier-Stokes equation in shallow water. So regarding the nonlinear Schrödinger equation, the system we develop is a system in nonlinear optics, and has already a paper published at the end of my PhD in Sapienza, University of Rome, and is on physical review letters, and talks about the way to, it is essentially the first realization of a neuromorphic computer using waves, nonlinear waves. Instead, this system is a system that we are developing in Apoha, this scientific startup based in London, in which we want to show that using propagation of waves in shallow water, we can actually achieve the realization of a neuromorphic computer. And the name is super fancy. It's a name that puts together the best of the two words that I love in physics, that is hydrodynamics and photonics. In the further presentation, I'm going to skip all the photonic details because are far away from the scopes of this conference, and I will focus much more on the hydrodynamical part. So this is the outline of my talk. I will first talk about this theory of neuromorphic computing by waves in optics, in which we use Kerr crystal, so a crystal in which the propagation of light is ruled by the nonlinear Schrödinger equation because it undergoes self-focusing nonlinearity. And then I will show you instead a proof of concept of the same system done in acoustics, using propagation of acoustic wave in shallow water modeled by the KdV equation. So let me start with the optical part. So for the optical part, we developed this system called the single wave layer feed-forward network. It's a system that is sketched quite well in this image. So we have at the beginning a continuous wave laser. This continuous wave laser impinges on a spatial light modulator. Spatial light modulator is a particular optical device that is able to imprint on every pixel a different phase in the beam. So after the spatial light modulator, the beam becomes structured, having a different phase added to every pixel. Then it propagates to the far field, so you can consider like having a Fourier transform, and it is superimposed to another CW beam that acts as a bias term. So a term that we use to get access to the nonlinearity. After, there is the propagation in the nonlinear medium, so in the nonlinear crystal, in which we have the Kerr self-focusing nonlinearity, which is ruled by the nonlinear Schrödinger equation. And the final layer is the layer of the channels, which are essentially just clusters of pixels on the CCD camera, so clusters of intensity of the image at the end of the propagation of the laser beam. So the neural network analog is exactly this one. So we use the SLM for the input layer, so to do the encoding. So our encoding is actually free space propagation of plane waves. And then we have a bias term that we use to enhance the intensity, so to get access to the nonlinearity into the crystal, because the nonlinearity into the crystal is a nonlinearity that is intensity dependent. After we have the propagation in the crystal, and after we have the output layer with our channels that are the channels on the CCD camera. And then the learning occurs when we superimpose these channels in output. using a proper array of weights beta, which is the array that defines our learning. So once we have the array, we can say that we did the training. So here there are even more details. I don't want to go, let's say, too deep on this, but just to let you understand. The way of encoding we did is called binary encoding. So essentially, if we consider an example like this, which is the interpolation of a sinc function, a function sin x over x, but we can consider other examples. We also work on classifications task, or we work on logic gates. But in an example like this, the training set is actually the set of numbers on the y-axis, which we can call t, and to every value t, we can associate a value x, which is essentially the argument of our function that gives us t. This value x can be decomposed in a binary decomposition in which all the waves of the binary composition can define a string. This string is the one that will define the kinds of phases that we are going to trace on our SLM. So our SLM will associate to every digit 0 a phase 0, to every digit 1 a phase pi. After that, propagation in the far field, as I told you, this means that we have a bunch of pixels propagated, so a bunch of rect functions propagating, which means that we actually get plane waves. So long story short, just to cut a little bit, we collect the array of the output channels. For every point, we get an array that will define a column in a big matrix that we call response matrix. It's the matrix called H here. So we want to find this weight beta such that this equation holds true. But in the condition in which the matrix H is actually a square matrix with non-zero determinant, this means to solve this exact equation, which is the equation that gives us the exact learning condition. So we just invert essentially the matrix H and we get beta from the training set. Once you have this, we have that the learning is done. And here you can see indeed the same example in different conditions. So this is just the propagation of the bias term, which is actually a rectangular shaped beam, very well studied by Kennedy here when he studied the Dunbrick problem, which is able to develop at the beginning diffraction by edges, and then it goes on and it develops different kinds of rock waves like peregrine-soidons and so on and so forth. So we accede to the nonlinearity of this system, and this is what happens instead when we superimpose to this rectangular shaped beam the superposition of plane waves that I showed you before. That is the one we use to do the encoding. So this is what happens when we use as a number of channels, a number of input channels, a very low number, compared to the number of training points. So the number of training points here is 200, the number of channels is 20. You can see that the network tries to follow the shape of the sinc function, but it doesn't work very well. The red circles are the exact points, while the blue dots are the points computed by the network. Instead, when we consider the exact learning conditions, so our matrix is square, and the determinant is not null, so we can actually invert the matrix, we can see indeed that the learning is exact. So there is a first transition to get an exact learning, and is the transition in which we need to have a number of channels that is higher or at least equal to the number of training points. But there is a second transition that is actually much more interesting for our purposes. That is the nonlinearity transition. So all of this is done at high nonlinearity. So for a nonlinear parameter here, chi, that is high enough. But if we consider a parameter chi that is not high enough, we can see that even in the case in which the response matrix is square, we don't get to the point in which the rank is maximum, so the determinant is non-null. We get to this point beyond a certain nonlinearity threshold. So this teaches us something important, and it's that we actually need complexity, because we need nonlinearity. We have a nonlinearity threshold to overcome. So we need a nonlinearity that is high enough to say that we generated a neuromorphic computer. So now I finally move to hydrodynamics. This is the kind of model that we are actually considering. And then I will show you a very simple, even if meaningful, proof of concept of this model, considering just the KdV equation and just a logic gate, which is the simple task we can actually achieve. But this is what we are actually using right now to develop our system. I will show you why. It is the KBK equation. It's an equation that puts together in the first two terms the Hopf equation. For the one who are not experts of it, I will tell you very briefly what it means. The Hopf equation is the equation that is able to model the surfer wave breaking. So this equation can be regularized in general in two ways, either in a dissipative or a dispersive way. If we consider a dissipative way, we have actually the Burger's equation, which is able to smoothen the wave breaking through dissipation, or we can have the KdV equation, which is able to regularize the wave breaking by very rapid oscillations. The KdV equation is also interesting because in the moment in which we're able to balance the dispersion and the nonlinearity, we actually get shaping invariant propagating waves called solitons. The last term instead is a term able to generate a little of chaos in our system, which is the Kuramoto-Sivanshinki term referring to weak turbulence. So in a model in which we consider the dissipation and the turbulence just as perturbative, we can build our system as follows. So we do the encoding using low amplitude Cnoidal waves, so waves that are essentially sinusoidal waves, in which we use the different parameters to encode information in our system. And then, since these waves having low amplitudes always have sort of a low velocity, we can consider also the collision between these waves and a soliton, which has always a much higher velocity, so a soliton will be sent after the encoding waves are sent. So a soliton that is an hyperbolic second, like with the mathematical expression reported here. In this system, I would like to stress that even if you see 3 different parameters per wave, it's not true that we have 3 degrees of freedom. The degrees of freedom are actually 2. And for us, we use as degrees of freedom the amplitude and the wave number. So the velocity is actually derived directly from the Riemann problem. And because in the Riemann problem, the 3 Riemann invariants are dependent from each other. So in a situation like this, what we can see compared to the optical system is that we don't need to use an SLM. An SLM, it's not a crazy expensive tool, but still is not comparable to generators of acoustic waves. And so we have a minimization of the electronics in our system. And also, which is very interesting, and we are actually right now understanding how to tune these parameters, tuning the dissipation and the turbulence in our system means essentially tuning how much first, let's say, the time t of our system interacts with the time t plus 1. Because every time you send encoding waves plus your solidon, you create a collision, and then you do your detection. If you have weak dissipation, this weak dissipation will destroy completely the contribution of the deflection into the trough. Okay, so tuning these parameters, we are actually moving from an artificial neural network with recurrent architecture to a completely feed-forward architecture. So again, this is just a proof of concept, but I think it can be interesting for the purposes of this talk. And I will go now, I will show you how to build a hydrodynamic extreme learning machine, so on reservoir computing with a complete feed-forward architecture, using just a pure KDV model in which we don't consider any refraction because we consider our trough as infinite. So in this case, I mean, simplest case, again, no dissipation or turbulence. About saturation, I didn't talk. Sorry that I didn't remove this part. But it's an extra layer of nonlinearity you can put in your system if you bring your photodiode or camera in the detection to the saturation regime, because it follows nonlinear function. So we are not considering anything now at this point. We're just considering a pure KDV equation, so an opt for nonlinearity plus dispersion. We do our encoding, as I told you. And we want to realize an XNOR gate. So a gate with this truth table, in which our encoding is done as follows. So we have two Boolean variables, A and B, and two possible values, of course, 0 and 1. The nature of the variable is encoded in the k vector, so in the wave number. So k1 for A and k2 for B, as you can see, indeed, is always constant, while instead the value of the amplitude encodes the value of the Boolean variable 0, 1. So when it's 0, you have absence of the wave, and when you have 1, you have amplitude 1/4. The solidon instead is fixed for any conceptual experiment we want to do. So in a situation like this, to do our training, we need to establish what is our target. So to establish what is our target, we need a mathematical model of our system. And so the best way to do this is to move to a canonic basis, is the easiest way. So in a canonic basis, I'm just associating to every versor of a four-dimensional real space a combination of the two Boolean variables. And in this way, I do the same in the output. I say that true is the first four-dimensional versor, and false is the last four-dimensional versor. In this way, our target is actually a projector. So again, the encoding I told you, the reservoir will give us as output voltage or intensity peaks. Here we consider voltage because we're using a photodiode, but it's a matter of how you want to build your physical system for the detection. So let's say voltage, but it's the same of the intensity patterns I showed you before. And the decoding is well done, so we can say that the network is actually learning when we have as a matrix of weights, a matrix W out, that if xj are the voltages at different time that we get every time that we send a superposition of encoding waves, okay, our yj is such that it satisfies this identity, which becomes, again, in the moment in which we consider just a square matrix, it becomes a simple matrix equation. too fast. Okay. So this is what happens in our simulations. You can see on the x-axis the only longitudinal. The only longitudinal variables that we are considering in this system, and on the y-axis the time. The intense peak that you see is always the Cnoidal, and you see that there is always a collision between the Cnoidal and the low amplitude Cnoidal waves in the middle of the trough. Okay, so these are the 4 different cases, and these are the points we use to build our response matrix. So in the point x equal 50 that you saw before here, okay, we trace the one-dimensional plot, which is this one, and we choose 4 points, which are always the same 4 temporal points, but of course it gives always different water rates, okay? And these are the values that we are going to put into the response matrix here. So the first 4 points are the first column here, second 4 points, second column, and so on and so forth. Okay, we can see the determinant is non-zero, even if it can be improved, and we are actually doing this using different encoding and decoding conditions, thanks to the collaboration with a group in Oslo Met, which is actually working on evolutionary algorithms to increase the value of this determinant. But anyway, for now, it's good enough to say that we are in the exact learning condition. And so for this reason, we can, when we consider a case in which the bias term is equal to 0, we can compute finally this matrix W out. We compute the matrix, and we are able to see that every time that we compute now the output from our network as this linear system here, okay, we always get the values encoded in the 4-dimensional basis that we expected to get. So let me conclude. What I showed you today is that nonlinear waves properly used can actually learn and compute, that our optical nonlinear wave reservoir works only if the nonlinearity is high enough, so it's related to the complexity of the system. That, and there is an extra layer here that I didn't tell you, but we have a different nonlinearity threshold for different encoding, so exactly what you were talking about before. Also, the number of initial instances changes the requirement for the complexity of the system. That also an hydro-optical nonlinear wave reservoir can be engineered using traveling wave solution of the KBK equation, and so this way that we are trying to show that complexity can solve complex problems. Thank you very much for your attention.
Thank you very much. Any questions? Yes, Davide.
Thank you. I actually have 2 questions. The first, maybe you gave a quick comment in the conclusions. So you said, so my question was related to the nonlinearity intensity that you need. So based on the signal that you want to reconstruct, do you need different nonlinearity intensities?
Yes. So we showed, for example, I think I have it here, in the, let me go on because these are just the extra slides of, okay. So for example, I showed you before that for the interpolation of the sinc function, we needed a chi parameter of the order of 20. Here, in which we are doing classification of 400 different abalons, we need a nonlinearity threshold that is higher than 400. So the requirements on the complexity of the system are for sure related to the encoding and the problem we want to solve.
And so how do you know a priori? How much would you need?
A priori, I would like to know that. The problem of this work is that, at least right now, even if it's just theoretical, but it follows a very deeply experimental approach. And for what I saw, and maybe I'm completely wrong, it's essentially the approach that people in computer science are following when they want to build an artificial neural network. They just tune the parameter in a way that at a certain point the network works, they're happy and they go on. So this is what we did at the beginning. So we saw that we do different simulations, we get different values of the nonlinearity. In one case it works, in one case it doesn't work. And we move on. We are able to trace this plot here, and let's say we are happy, we go on. I'm personally sure, since I worked for many years on the theory of the nonlinear Schrödinger equation, we can use methods related to filamentation and Lyapunov variational methods to solve the problem, at least to give an initial estimation of the kind of nonlinearity you need. But it's something we are still working on. And there is another point that I'm actually also very sure that if you increase too much nonlinearity, you actually find another threshold. So a threshold that tells you that you get to a chaotic regime and that actually you're able to predict anything. So for example, in the example I showed before, and Professor L knows this very well, if you get, for example, to the regime of a solid on gas, I personally think if you get to that regime, you cannot do any kind of machine learning, neuromorphic computing again. But still, it's work in progress.
Thank you. And the last question was that could you use, if you use an integrable model, could you use any tools from integrability maybe to try to optimize, for example? I mean, is integrability actually helping you in some sense?
Actually, the optimization we have done till now, it's on the other direction. So we actually try to go far away from the integrability, adding noise, or again, adding saturation regimes which are not integrable anymore, and so on and so forth. And we saw that even if we go away, maybe, from the exact learning condition, because you add noise, so you add something that is stochastic at the end. Okay, so you must, without maybe, you must go away from the exact learning condition. But since you cannot use a square matrix every single time, because square matrices are, in some case like this one, can be 400s times 400s as a dimension. Okay, so what you want to use is a reduced model of your system, and so you must use a model in which you have a certain degree of accuracy that if you're lucky is like 95%, or you will never have the 100%. And we saw that adding non-integrability to the system, so again noise, is actually performing very well. This is a work done also in a group working in Paris, where the PI is Professor Sylvain Gigan, and they created a system, and then we followed that work, and we were able also to create the same experimental system compared to the one in nonlinear optics that I showed you. But they just use random media, so they just use scattering and free space propagation, and the nonlinearity is just given by the saturation of the camera. So I really would like to work on the integrability, but all the things that have being done for now are in the other direction.
Thank you.
Thank you. Questions?
Quick one. Probably I didn't understand it. At the beginning, you mentioned that the advantage is going from a discrete system to a continuous system using this approach, right?
The analog computer?
Yeah.
Yes.
But then when you talk about the camera, the CCD sensor, that's discrete to a certain extent because it digitizes the information in bits, and so to a certain extent you go back to being in a discrete measurement.
Yes, no, I totally agree. So you need to discretize your phase space for now, for what you're doing, because you need to build a matrix, and a matrix must have channels. On the other hand, it's also true that I, for now, showed you in details just a logic gate, which is the most discrete things you can find in computer science. So it's kind of misleading, but it was the only thing I could show you. But for example, if you consider the interpolation, you can do regression with this system, and you can decide arbitrarily how to discretize your data. And this means that, yes, of course, to work in the real world, you need discretization, but if it's arbitrary, can it be considered as continuous? Maybe.
Okay. Any more questions? Actually, have any question on online? No questions online? No, okay.
Too late, people are sleeping.
I have just like a short question through a comment. I remember something that goes back to probably over 20 years ago, so I can't even make a reference to specific details, but I remember Mark Ablovitz wrote a paper on logic gates and solitons. I think he has a patent as well on that. So is what you showed any related to that? Or?
Yeah. What I showed is absolutely ready to, yeah, for sure from ready to Ablovitz's theory. It's a theory that we developed at the end of my PhD. It was heavily based on the theory of nonlinear Schrödinger equation. But honestly, now I don't recall this paper on logic gates made using solitons, so I cannot answer to this question. Okay. But I will check.
Yeah, I mean, I've seen the paper many years ago, and yeah, probably you won't remember anything about that. Anyway.
Thank you.
Okay, thank you. Any more questions? Okay, if not, let's thank Giulia again and all the speakers today. So, I think now before a networking reception, we have, so we have an opportunity to ask questions, to get an open discussion and ask questions to the speakers or make any